Hello, everybody. This is another Thursday opportunity to pick something interesting. This is the Prague Seminar for Mathematical Physics. Today, with our kind guest, Tomáš Procházka, we're going to deliver a very interesting topic. And as far as I know, this is a topic which hasn't been spoken for a desperately long time in our episodes. So Tomáš topic is being born right now. Will be about that equation and 2D conformal field theory. And one last piece of information in regards to Tomáš. He's currently a researcher at the Physical Institute of Czech Academy of Sciences. So we are very glad you came to us, Tomáš, and the floor is yours.
Yes, thanks for inviting me. Yeah, so I want to talk about I just wrote the equations in two-dimensional conformal theory. So from math perspective, you can also kind of rephrase it as some kind of aspects of representation theory of Virasoro algebra. So the main symmetry algebra. So you don't really need to know like two-dimensional quantum field theory and so on, but because the most of the discussion is more like representation theory of the algebra that I'm going to write. But it is underlying symmetry algebra of two-dimensional conformal theory. So if you have 2D CFT, there are two commuting copies of this algebra, and this is what I'm going to study in most of the talk. Okay, so so one way that you can think about this algebra for c equal to 0. So if you ignore this term, you have just the usual Lie algebra, which has infinitely many generators. Okay, and these are the commutation relations. So this part is often also called the width algebra, and then you can write a central extension of this algebra. So you can think of this C as being a central element, or
sorry, the L-subs are actually generators, not subspace.
yeah, they are generators. Yes, they are called L. Yes. You can think of this C as being kind of additional generator of the algebra that is central, or I would say my more favorite perspective is that this algebra actually, because this algebra is a part of larger family of algebras, which are called W algebras, and those algebras are not Lie algebras in the usual sense. So they are kind of algebras whose commutation relations look like this. So there are certain generators, but the right-hand side is not necessarily linear in the generators, but can be more generally some element of what would be the universal enveloping algebra of this Lie algebra. Okay, so these such algebras are called W algebras, and they seem to appear naturally in physics. But in the case of Virasoro algebra, we are lucky because the part that is not linear, somehow if you think of C as being some number, so the part that is non-linear, you can just think of it as being another generator. Okay, so then you can think of it as being really usually algebra. But I prefer to think of this as being a number. Okay, but this is just like how you think about it. Okay, so now if you want to study representation theory of this, and if you want to mimic the standard like Cartan, Weil, or the representation theory, you would pick something like Cartan generator, and then try to think of other generators of algebra as being some ladder operators with respect to this. And this is what is usually done. So people usually pick this L0, possibly C, you think of C as being another generator, as being Cartan subalgebra, and then you have infinitely many other ladder operators. So if you look at commutation relations of L0 with all other Ln, this term does not contribute. So then you see that basically the other ones increase the L0 eigenvalue by multiples, by integers. Okay, so I have something like L0, L minus m, m, L minus m. So you see that the L minus m increases the eigenvalue of L0 by just integer by m, and so on. So then you can study high-state representations. So you can study, let's say, some modules which are generated by the high-state vector, which I call delta. So I So if I specify that this high-state vector is eigenvector of should be delta, that should be some should be eigenvector of L0 with some eigenvalue, and then annihilate it by all positive annihilation modes, and then I let the negative modes act freely, then I get the Ver module and I can study the representation theory in the standard way. Okay, but if you are familiar with the representation theory of simple, complex simple algebras, you know that this example is quite different than the usual SLN algebras, for example. In fact, that the Cartan algebra is extremely small and the number of ladder operators is very large. So although the algebra is infinite dimensional, the Cartan subalgebra is just 1 or 2 dimensional. Okay, so this is kind of, and actually the reason why we can say anything about the representation theory is that the structure of these ladder operators is like very simple, but still it's kind of strange situation. And the question is if there are some other elements that we could add to this like L0, which would commute with it. Okay, and so the question is if there is something bigger. Is anything bigger? Algebra. Okay, so this is one of the my questions, and of course this question is very old and it was studied since 90s or even 80s. So the answer is yes. And there are other things that we can they are not really anymore generated, but there are some kind of, you can think of them as being elements of the universal and helping algebra, which commute with this L0, and it's very interesting to try to study their spectrum and diagonalize them in representations and so on. Okay, so this is like what my talk is about. So Bethe equations are some kind of algebraic equations which allow you to diagonalize this bigger Cartan subalgebra, let's say. Okay, any questions? So yes, I had short comment in my notes, but maybe it's not so relevant here. Like, what is the like physical interpretation of L0? But I think still scary. So you can, in physics, you can study the conformal field theory of different Riemannian surfaces, and the standard place where you would study it is like infinite cylinder, and in that case, L0 is just Hamiltonian. It's just time translation generator, which just evolves your system from time t0 to time t1. So this is the meaning of this L0. And if you map it by exponential map to like the complex plane, then the minus infinity, like in minus infinity in time, corresponds to the origin, plus infinity corresponds to infinity, and then these constant time slices correspond to circles around origin. And in this picture, L0 is kind of evolution operator that goes in this radial direction, and then the eigenvalues of L0 here you would interpret as energies of your physical system, while in this case you would think of eigenvalues of L0 as being scaling dimensions of local operators, which if you don't know what it is, you don't need to know, but for those who know some quantum field theory, that's what L0 does. Okay? This is like the meaning of L0.
And the Real-Zero algebra is related to wave equations of sigma models, but to which geometry? I don't know. To which? To the
geometry, the Real-Zero algebra is something that you have
function point.
You have quantum field theory, let's say, on any Riemann surface. You can look at some more neighborhood. You have some local operators, that we could insert there. And irrational algebra is something you can define locally. So there is some special local operator that plays very important role in the conformal theory, which is the stress energy transfer. So it's a special object that every two-dimensional conformal theory has, and you can do some kind of action of this T on all local operators. So what you do is to take your local operator O of Z, then T of W, and you can kind of calculate contour integral with this T of W around O of Z.
Yeah, Tomáš, I understand, but
And then that gives you action of such algebra on the space of
the specific Virasoro is connected. Is the specific this Virasoro algebra connected to a specific, let's say, class of Riemannian surfaces?
No, it's a local thing. It's like around every point.
So you
have
I can have any plane this. I can have to plane this any function.
Yeah, you can have arbitrary choose.
So it is not. But you don't say that this is connected to the cylinder.
So
I meant.
I mean, but so let me say like this: you have this general stress energy tensor, which is something that exists locally on any Riemannian surface, but then this else corresponds to Fourier modes of this T. And if you want to write Fourier modes, you need something like a circle with respect to the Fourier expansion. So that's kind of what will be clear in this picture. But if you choose on any Riemann surface, any point, and around it you choose locally coordinates like this, then you can, by exponential map, you can map it to cylinder, and then you will have these modes. Okay, so this is true in kind of any local coordinate system and around any point. Okay, so actually you have like many copies of Virasoro algebra if you want.
Is there any simple interpretation that this allows from m is equal to minus m?
Yeah, then they are kind of conjugate. So if you look at these computational equations, somehow the Lm and Ln, they are kind of paired to L0. So also from this relation, you see that if you act with L minus m, you increase L0 by m, and if you act with Lm, then you again increase it. So they really act as kind of creation annihilation, but they are like paired. The L plus minus m are like paired together. They form kind of SO2 subalgebra. No? L0, Lm, and L minus m. They give you this triples. Like not directly, but if you quantize Nambu-Goto actions in such a way that you get conformal field theory, then you have it. Because every conformal field theory has. But this is kind of the universal thing that every 2D CFP has. Okay. Yes.
So for any genus and for any number of functions, there is a way to glue this local algebra.
Yes, and I think the mathematicians who study vertex operators algebra, they study exactly how to glue it and all this. Probably, yeah. So you see, you have a lot of games to play. Like if you have some Riemann surface, some genus, then you need some local operators insert it. O1, O2, you can kind of integrate the stress energy tensor around O1, which gives you actual Virasoro algebra, the local operators at this point. But then you can kind of go to deform this thing, and you see that action on this is somehow related to action also on other ones. So this is what the physicists would call word identity, some kind of consistency relations for relation functions, where you really have, there are some kind of intertwining relations between these different representations of Virasoro algebra with different checkpoints and so on. Okay, so there is like nice geometry. But today I'm really talking just about this. So that's kind of really looking at it locally around one point. So so we can think of it as being like some small disk around origin in the complex plane if you want. So as I already mentioned, this Cartan subalgebra built from L0 and ABC is very small, and because of this, the representations are very degenerate from point of view of L0. So if you study characters, so if you have some, let's say, irreducible representation, and you study trace of Q to L0, so basically you study how many vectors there are, what are the dimensions of subspaces of L0 with some given integer or whatever value. you will find that these subspaces have like increasing dimensions. Okay, so for example, my favorite class of representations correspond to C equal to -22/5. So this is some kind of numerology. Why is it this number? But it's one of the smallest representations of the algebra. So there we have two interesting isolated states. So primaries, okay, this is the primaries. One has delta equal to 0, and another one has delta equal to 1/5. So this is a little bit like when in complex simple algebras you can study Verma modules, but then for some special values of highest weights, you know that the Verma module is not irreducible, so you can ask yourself for which highest weights the module is reducible and what is the simple quotient and so on. So here you can do exactly the same play the same game. So by tuning this C and L0, you can make your irreducible representation smaller than is the generic Verma module. And for these values, you get one of the smallest things, but they are interesting for many other reasons. Okay, so this is my choice for concrete examples, but you could, study many other examples. So for example, for these two choices, the character can be written quite simply. Maybe let me put here minus C/12. This is just constant shift, which is again physically motivated from this Hamiltonian picture, but also mathematically. These characters, as Svatya mentioned, you can study it on different Riemann surfaces. So, for example, when you want to study it on torus, you would like your characters to transform nicely under like mapping class group of the torus, and it is correct choice of this shift. You will actually see that these characters are representations of the modular group and so on. So yeah, if I choose this to be definition of the character of representation V, then for this concrete case, the two characters look like this. So this is delta equal to 0, and the other primary is q to -1/60, and again q to the fifth, q to the fourth, q to the fifth. And so I'm using notation for this q Procházka, q to j, q to n. Infinity is just an infinite product, let's say over L from 0 to infinity, 1 minus q to j plus L. Okay, so it should be something like this. So for example, we choose this to be, let's say 0 and 1, or something simple, then you product of 1 minus q to all positive integers, which is just the 1 over the dedicated beta function. Okay, so this is kind of well-known function in this theory, let's say, of representations of modular group and so on. Okay, so this is just some infinite product. It's called Q of our symbol. And the characters of these two nice and simple representations can be written in this very compact form as just product of two Q Procházka. If you look at the expansion around q equal to 0, so you are counting how many states there are at lower values of L0, and the first one starts +1 plus q squared plus q cubed plus q to the fourth. That means not right, and there is 2 times q to the 6, and again I skip some terms, 6 times q to the 12, and so on. So it's some kind of collection. The coefficients are some collection of non-negative integers, which are counting the dimensions of the eigensubspaces of L0, and you see that they are increasing. And similarly for the other one, I have one called q plus q squared, and many other, then it is 7 q to 11 plus 9 to 12, and so on. And these numbers are increasing. And it might seem that they are not increasing too fast, but actually, you can look at asymptotic growth of these coefficients, and you find, so there is something in physics called Bernoulli formula. So that is something that kind of asymptotically estimates how large these numbers get. So what are the degeneracies of eigen, like subspaces of this L0 for large values? So the coefficient of Q to M in this thing goes roughly as exponential of 4 pi times square root of M times CF divided by 24, where CF is C minus 24 delta N. Okay, this is just kind of to see how the degeneracy is. So for every, there is a nice class of representations which people call minimal models, and for those we have finite number of interesting primaries. One of them has the minimal dimension. In our case, this is -1/5. So then this C effective, this is what people would call effective central charge, is given by this formula, and it controls the asymptotic growth of the numbers of states. Okay, at large. So you choose the subspace of L0 to be
the upper bound.
no. So I choose L0 to be proportional to M plus some maybe -1 or 60 or something, roughly M. Then I look what is the dimension of the subspace of L0 with this eigenvalue, and it's growing as exponential square root of M times some number which is determined purely by the central charge. Okay, and one way how we would prove this type of formula is exactly to use this modular transformation property. So you can study the theory on torus, where the complex structure of the torus is related to that parameter Q, and then the limit Q going to 0 or Q going to 1 are related by the modular transformation. You exactly know how these characters transform. So those functions of Q, they have very concrete and nice transformation property if you change this shape, this Q parameter. Okay, and from there you can kind of read off how this asymptotically behaves. All these things are nicely related to the numbers theory that is related to this modular transformation properties. So there is something called Rogers-Ramanujan identities, which is something that I guess Ramanujan found for these two characters. So there is not only a representation of these functions as infinite product, the way I wrote it, but there is also representation as infinite sum. And yeah, so writing it as product equals to sum is exactly what
Tomáš, you do traces or you do characters? You don't, because I can imagine that if I do trace as a sum of eigenvalues, that the eigenvalues of Q to the power L0 can be actually infinite, or can be add to something really not converging on the
So what I do,
character or trace?
I think this I would call character, but it is a trace of this Q to L0, no?
Directly, not regularized.
I mean, Q regularizes it. Okay, so I need Q to be in interval like 0, 1 for this or in unit disk in order for this to converge. Okay, but so yeah, maybe I should say this. I use this all the time, but let me say it maybe more explicitly. So this formula tells me that up to some overall shift in L0, which is some constant related to the central charge. Okay, so if you ignore this number, there will be one dimensional subspace with L0 equal to 0. Then there will be no state with L0 equal to 1. Then there will be one state with L0 equal to 2, two states with L0 equal to 6, 6 states with L0 equal to 12, and so on. Okay, so from this point of view, the spectrum of L0 is very boring.
It gives a spectrum of the compositions.
Yeah, of this L0. But so the spectrum of L0 is quite boring because here you see that it's basically all integers except for missing Q equal L0 equal to 1, and here the spectrum is all integers. But what is kind of non-trivial information are the multiplicities. So how many times does each what is the dimension of those eigenspaces? Okay, and this is exactly kind of subject of my talk, to try to find some other quantities such that you would be able to distinguish these states. So you have some nice 9 states with L0 equal to 12, but you don't have any good description of those states. And there is kind of a way how to describe them better by adding some other elements, let's say of the universal analytic algebra, which commute with L0 and which kind of remove this degeneracy. Okay? Any questions about this? And you see that asymptotically, the degeneracies really grow exponentially. So it's kind of a very big problem that you don't have a good way how to
We are
label the states.
moving these degeneracies iteratively, or
No, I want to introduce some other things, other operators, which will already remove it. So if you manage to diagonalize those, you can simultaneously diagonalize L0 and this, and then typically the eigenspaces will be just one dimensional. Okay, so that kind of solves it in one step. But the question is how to diagonalize them, and they have much more complicated spectrum than just integers. Yes, okay. So this is very standard thing that always you do in physics. If you have some system and some Hamiltonian which has degeneracies in spectrum, so it doesn't have simple spectrum, then you try to find a reason for it. And typically, there is some symmetry involved, like the symmetry that causes these degeneracies. Dobré, no i stíráte na no. Jo. Yeah, I'm used to from Germany. That we want to do this. So.
From academy wants to take it from the bottom to part and just go up.
Okay, that's perfect. Hopefully, okay. Yes. So there exists actually infinitely many other elements that you can construct, like in this Bressor algebra with commutative L0, but to write them, you need to work like in some completion of the universal enveloping algebra. Okay, so it's a little bit similar again in the representation theory of complex simple algebras, where you have this higher Casimir, or you have Casimir operators. You have some quadratic elements in the universal enveloping algebra and so on, which commute with all generators of the algebra. But in order to write them, you have to work in the universal enveloping algebra. So here the situation is similar. So apart from I1, which is just the integral, as I mentioned, these L's are Fourier modes of this object T. So the zero Fourier mode, let's say that I'm integrating over the circle of the cylinder. The zero Fourier mode is this L0 up to some constant shift. And then I can also calculate zero Fourier mode of something else, which is like T square. I will tell you roughly what it is. And that one turns out to be L0 square plus 2 sum of L minus M Ln plus some other fields. Let me write it just in this example, and then I will not write it anymore. And there is another one, I5, integral of dt minus p over 12 times dt. And many others. Okay, so now what does this mean? So, first of all, as I told Sváťa, if you have local fields, you have some kind of algebra with local operators, and there is operation of kind of like fusion of two together. So if you have P W, I could try to send W to Z, so kind of fuse them together to produce something like T squared. But actually, these two T's, the correlation functions, so you can study basic observables or basic things in conformal field theory, which is kind of correlation functions. And if there is a correlation function with many other operators, that's some kind of meromorphic function of the insertions of this point. If you look at those correlation functions, if you try to send one T close to another T, all these correlation functions diverge, okay? And they diverge in very concrete way. And the way how they diverge is exactly encoded by the Virasoro algebra. So this is kind of conformal field theory, a kind of description of all these things. You specify what is the singular behavior of correlation function when some of the operators come close to each other. But this is not what I want to talk about. What I want to say is that there is well-defined way how you can send this the W to Z after subtracting the singularity. And that produces for you some kind of local operator which you can call T squared. Okay, so I can out of the W I can produce T squared. Okay, and it's called in the notation that I'm using. It's called TT. Okay, it's actually not too difficult. It's really just this. It's the contour integral. Z over 2 pi I Z W over Z minus W. So we have this. Okay, so it's just I encircle this around W which is Z, and this prescription kind of extracts only the regular term in the Laurent expansion of this meromorphic function, and that's exactly what I think of T squared. Okay? There are some poles when they are near to each other, but those are kind of ignored by this formula. And there are some terms that vanish in the limit, and these are also ignored. And this one really extracts just the first regularities. Okay, so this is not TT, but it's roughly like T squared. So you can construct in conformal field theory operators which are like higher powers of this stress energy tensor, and also of its derivatives. So you can also study operators like derivative of T. Okay, and in the language of these Fourier modes, the Fourier modes of these operators can be written in terms of Fourier modes of the T itself, because everything is constructed out of T, but the resulting thing is nonlinear in L. Okay, so that one is kind of residue calculation. No? This one.
So I just asked the hidden proofs. Yeah, so just complex analysis in Banach values for Banach value functions or reactive value functions. Yeah.
You can think of it as a
residuous theorem theory.
Yeah, so this calculations that I'm describing here, that is really like residue theorem. I don't think you really need to use some Banach whatever. You can just think of these correlation functions as being just Riemann surfaces with some decorated points, like labeled points, and to each such point you associated like a letter of alphabet like T, and such a thing produces some meromorphic function of these positions. Okay, and then at the level of these meromorphic functions, you can use just the usual complex analysis. You don't even need to know anything about like Hilbert spaces and things and so on. You can just study how these meromorphic functions, what are their poles and so on. Okay, but that would take me a bit too far. But sorry. Yes, good. So. What I'm writing here are kind of roughly, if you think of this TT as T squared, there are some kind of differential polynomials in T, because in conformal field theory with just Virasoro algebra, I don't have any other kind of universal class of operators than just T and its derivatives and polynomials in this. Okay, and there is some kind of grading in this space of operators. So this T has kind of degree 2 which is related to many things, but it's kind of a natural dimension of the stress energy tensor. Then, for example, this object here would have degree or dimension 4 and so on. Okay, this one would have dimension 6 and so on. And then you can just ask yourself what local operators I have of each degree.
So Z increases by 1. Right?
Yeah, derivative increases by 1, exactly. So you have 2, 2, and 1, 1. Okay. So for example, in degree 4, you could write t like t squared, or you could write d squared t, second derivative of t. Okay. But the thing is that if you take the zero Fourier mode, the zero Fourier mode of the total derivative is 0. Like integral of the derivative is 0 over circle. So this doesn't contribute. So there is like unique choice of zero mode of something in degree of dimension 4. Okay? So there's nothing else to choose here if I really want to construct something like this, but in the dimension 4. Okay? And then after I do this, then the next dimension, again, in dimension 5, there is nothing. In dimension 6, I could write the field of P, or I could write like dt, or I could write d squared t. You could also write t squared t, but these are related, and then you can also write d for t. So you can write list of all local fields that you can write just out of t and its derivatives. Okay, and it turns out that if you look at the zero Fourier modes, because it's the zero Fourier mode that commutes with I1. Okay, so that's the reason why actually I'm choosing the zero Fourier modes. But if you write them, then this one is the total derivative. Then these two are related by some relations, by some kind of manipulations like integration by parts and so on. So there are basically two independent ones that you can write. And then if you require such a thing to commute with this one, then this uniquely determines the relative coefficient between them. Okay, so up to normalization, there is a unique choice in dimension 6 that commutes with both I1 and I3. And this goes, I think mathematicians say that it's not really proven. Yeah, I always use this grading to correct. So well, I heard from some mathematicians that still has not been proven. Okay, I'm not sure about that. Like situation of this, whether it's proven or not, but I know that if you calculate it for first like 30 degrees, then there is always like unique choice in each dimension or degree up to the overall normalization, because you can always rescale it by some constant. Okay, so there is this in every even degree, there is always unique choice, and in every odd degree, they are all total derivatives, so there is nothing. Okay.
Is it conversation holds for KDV equation?
It's really KDV very closely. Yeah, but KDV, that's what I would say maybe next. KDV is kind of classical limit of this, and there you have same class of things. But the KDV is something that you get in the large C limit, so C going to infinity limit. So the KDV conserved charges, which I will write momentarily, they don't see these things like +2. The KDV will only see over 12 and so on. Okay?
Or you have simplicity in the discussion. So the product of T, C, and DC is associated with generally the answer.
The way I define it like this, it's not associative, but it's kind of almost. So the non-associativity is measured by some. There are kind of concrete replacements of like associativity conditions. I can show you. If you have 3 operators and 1, 2, 3, I can integrate this around this, and then this around this. And you can do some kind of contour deformation where you can write it in 3 different ways. So there is like a concrete way of writing associative.
Associated within this integrals.
So at the level of these Fourier modes, it is associative, but at the level of these things, it's not really. So you don't have like A, B, C is not, let's say A, B, C, but it's known what is the difference. So this is known in terms of some other operations. Okay, so you don't need to extract just the zero Fourier mode, but also other ones, and then they enter these relations. But it's like well-known kind of replacement of associative. I mean, you will still call it associativity, but it just does not look like this, but it has some other terms. Okay, but at the level of Fourier modes, if you work in this universal enveloping algebra, if you study representations, there it's really associative. Yeah, and by the way, this thing looks like kind of quadratic Casimir operator or something, but there are two differences. One difference is that there are these infinite sums because the algebra is infinite dimensional, so you really need to consider some completion of the universal enveloping algebra, but such objects are well defined in the high-state representations because there is only a finite number of ends which give something non-zero. Okay, so in the Verma module, this is well defined. Okay,
But Tomáš, may I ask you this? L can be total associated.
Yeah, in LCS. In LCS.
But this piece, you compose this piece on the right hand side behind the integral as really composition of operators, so it is also associated.
Yes,
And you do the associated probably when you do the residuals or not.
yeah, like so.
ICTP, yeah,
So if you want to think of this kind of description in terms of some operators acting on some vector space, then you have to do it with respect to certain regular ordering because you have to do first things that are more inside and things that are more outside. So if you, for example, exchange the two, or if you want to do first these two and then the other two, then you have to worry also, about this ordering. But it's kind of
after composing, you must do the ordering which destroys the associated.
I think the problem with associativity is that this definition is not symmetric with respect to first and second. And because of that, also, yeah. I mean, I can show you how this formula looks like later. Okay, it's like a well-defined and concrete thing. And the point is that in the end, correlation functions are always meromorphic functions of these Z1, Z2, Z3. So you can also exchange them. You can put Z3 to be smaller than Z2 and so on. It's all like meromorphic function. But if you want to translate this Fourier mode language, you really always have to order things that as you go from right to left, you will go from inside to outside, just like
From expectation, it's strange to say that composition is not associated. Composition.
I mean, you can call it. You can say it's associative.
You don't do only composition of endomorphisms, but you use composition with some parameter in the ordering and wild things.
I would still go
Which is defined certainly, but it's not time easy to show it.
I would
Technically,
associative.
the definition is technical.
That the algebra is associative, but the way that the associativity looks like, if you write it in equations, it does not look like that ABC is ABC. This is no longer true, but there is some kind of generalization of that formula that works,
Yeah.
and that expresses the associativity. So I'm almost out of time. And yes, so there is this classical picture, which is quite nice. So since there was a question about KDV, and since I don't really need to reach some specific point, but let me really ask you, like, who saw, or is there anyone who did not see in their life, like Schrödinger, one-dimensional Schrödinger equation? Is there someone who doesn't know how it looks like? So, okay, if everyone knows, then it's good, and I can show you kind of what is the classical interpretation, what is the classical non-quantum limit of this. So you can consider second order differential operator. You can think of some Hilbert space like on circle with coordinate x. It does not really matter so much how you choose this x coordinate. You can study it also on the real line, imposing some decay conditions at infinity, and you can study like this function analysis of the second order differential operator with some fixed potential. So this view on circle, it could be just some periodic functional view, or you could study it on infinite line, and you could study some nice physical potential. And you can associate to every such potential some spectral data, some information about spectrum of the differential operator. So there can, for example, be some discrete eigenvalues, like discrete spectrum. There can be also some continuous spectrum if the potential is doesn't go to infinity and so on. So there is some collection, abstract collection of spectral data. The easiest situation would be, for example, if your potential u of x is like x squared, like a harmonic oscillator. In that case, that would be simple spectrum where the eigenvalues are equidistant. Okay, and they go overall, let's say half integers in some normalization. So now the question is, if given this such a problem and its associated spectral data, whether there are some deformations of this potential which give you exactly the same spectral data. So how much does the spectrum determine the potential? Okay, so this is some kind of what maybe mathematicians would call like inverse scattering method or something like this. So normal scattering is when you are given potential and you study some spectral data out of it, and inverse would be how much can I reconstruct the potential from the spectral data. And clearly, it's obvious that the spectral data cannot determine the full potential. Because, for example, if I just take my potential and do rigid translation by any distance, then you know that it does not change the spectrum. Okay, so more abstractly, if I solve differential equation d over dt1 u is dxu, this is trivial. If this means that I really shift my x coordinate by t1, if I solve this equation, then the spectrum is not changed. Okay, so definitely the map from here to here is not 1-to-1, but it's like many to one. There is at least this continuous one parametric family of changes of potential, this u, which doesn't change the spectrum. But surprisingly, people found there is infinitely more kind of degeneration. So the next simplest example is the KDE equation for the Maurice. So that says that if I again evolve this u so that it satisfies this nonlinear partial differential equation. Okay, so you can start at some given value of t3, say corresponding to this, and then you can solve this evolution differential equation for higher values of t3. So at every step we know how to change u. So the right-hand side tells you how the potential changes as I move a little bit in the t3 direction. Okay, so this is some kind of first order equation in t3, which allows me to evolve the potential. And it can happen that starting from this, it would produce something else. Okay, and the claim is that independently, like how much you evolve for how long in this t3 direction, the new potential will always have the same spectrum. Okay, so this gives you another one parametric family of u's which give identical to the same spectrum. Okay, so physically, people will talk about scattering of solitons. It's just like a picture. So if I choose some u of this type, and if I evolve it following this equation, we will dt1. This is like just rigidly moving the potential, so it's not doing much interesting things. But on the other hand, if I solve this nonlinear equation, then you would see that these kind of lumps or solitons, that they are actually starting to move. So you can think of a situation where they are at the beginning very separated, and then as I evolve it, they come closer together. Then at some point they can do something like this, and then they pass each other and go again to the opposite infinities. And the claim is that for every fixed time in this picture, I get some Schrödinger potential who has exactly the same spectrum as at the beginning. Okay, this is very like surprising and non-trivial statement, but it's quite easy to prove, okay, algebraically. And you don't need to know even too much about really what is the class of functions that you are studying and so on, because this really is something very algebraic, okay? And there is infinitely many of these. So there is the 5, the 7, and so on. And furthermore, all these flows in the space of potentials, they all commute, which means that if I start, so now this is my space of potentials. It's like some infinite dimensional very big space. I can evolve my potential for t3 seconds, in t3 direction, then I can evolve it, let's say, following this other equation for t5 seconds, or I can first do this, and then this. And the claim is that these evolutions commute, so it doesn't matter in which order I do it, yes?
So does this negativity do this negativity or?
Yes, it does. Okay, this is why I'm talking about it. Yes. This is classical version of that, okay? Good. And I'm really not so far from telling you exactly how it's related. So this whole, the equation for T3 is called KDV equation, and then this whole thing is called KDV hierarchy. Okay, so that's how they are called.
And sorry, KDV, what does it stand for?
That's the name of the guys, but I write it. For the lyrics. I even have.
Right, what was in Dutch?
Sorry?
What was in Dutch? It's called.
Sounds like that, no? But it was actually the first time this equation was written not by them, but it was written by Paul. This guy wrote it in footnote of this book in 1877. So very long time ago.
Yeah.
But the fact that these things give you this integrable systems and so on, I think that was only found in the 70s. So it took like 100 years until people realized that even in classical case, okay, so it's a very long time before people realized how beautiful these equations are. And it was discovered even not like by mathematicians, but I think like some physicists were studying really like some numerical experiments, and they found that something is behaving in a very strange way. And only from there they kind of distilled and find out that there's this like integrability, like very regular behavior of the solutions and so on. So it's a bit strange that people found it through numerics instead of like, analytically. But the equation itself. Okay, that will not be very clean. Yes, so let me say how those flows are related to this Virasoro algebra trial before. So actually, this infinite dimensional space of potentials is a Hamiltonian system. Again, I'm not going to explain this, but basically I can define Poisson bracket on the space of potentials. A little bit ugly. This is a little bit like kind of, in symplectic geometry, if you define symplectic structure, but I write it in terms of Poisson structure. So on this space of potentials, you can define this. There are different choices of Poisson bracket, but this is the one that is useful for me. And the relation to the quantum case is that if you write this if you study these potentials on the circle, and you look how this bracket looks like in terms of Fourier modes, so you just Fourier transform this equation, then you get again the Virasoro algebra. Okay, this gives you the term with central charge, and this gives you this first term m minus n times Lm plus n. Okay, so this is kind of how it looks like. So this is kind of a classical demonstration, like manifestation of this. There is some kind of relation to this Virasoro algebra, and then with a Poisson bracket, you can try to write those evolution equations as Hamiltonian equations. So you can try to write them as dt1 u of x is bracket of some Hamiltonian times with u of x and so on. Okay, and such a thing works with those equations if I choose I1 to B, and now big surprise, the zero Fourier mode of u of x, then I3 to be the zero Fourier mode of square of u of x and so on. So this is also related, I think, to what you asked, how do we construct them and so on. So in the classical limit, where you don't need to worry about this square of the thing and so on, we really have some like well-defined functions. You know, you can just study. You can just look for the commuting Hamiltonians, and again, for every you assign degree 2 to u, degree 1 to derivative, and that at every degree
Is U distribution with compact support?
you can think of it as being a smooth function.
No, no, in the Poisson bracket.
Ah, here, yeah, this one. Distribution with compact support. Like I think of U as being smooth functions. So then there definitely distribution with compact support.
Evaluate them in a point, I obtain numbers. So you say that you are actually defining Poisson brackets for numbers. UX is not.
No, you cannot. This is as usual, like in
numbers is distribution.
No.
Which might be, but it's weird.
So-
So I want to think of use as being tempered distribution.
So if you think of it,
Integrating by over smooth function, over smooth function times.
I wrote this data function, you know, so this is what you don't like, but actually,
And there are two functions more like integrate on the right hand side.
sorry.
No, I get.
Anyway, so I don't think you should think of the US number because you really need. So this is like in standard symplectic geometry or classical mechanics that you cannot calculate. You have coordinate and momentum, and you cannot calculate Poisson bracket of concrete points in the
No,
space. No,
that's why I
the
use
bracket is defined like on functions.
That's why I need distribution.
So this u of x,
meant in this way really.
this u of x is really my like kind of observable. So it's function that lives on my space of potential. So on this space, every point is some potential u, and then this thing is some function that lives on this space, and the value of that function, so x with x is 5, the value of that function is taking this potential at this point and evaluating it at x equals to 5. Okay?
What is the of x minus y? How do I subtract points from my?
Okay, then if you don't like this way of writing it, just do Fourier transform, and then you have just the Virasoro algebra, and then you are happy because there is no delta, no distributions and nothing. Okay, so that's just different choice of observables. If you don't like these ones, you can just talk about the Fourier modes. Okay, so for example, the L0 instead of observable which would be u of x, you would take observable which just takes u and integrates it. Okay, and you have no problem with this, no? On the space of smooth potentials. Yes, definitely. Definitely. So if I wanted to generate this, there are like procedures to generate this, for example, and the Laxter would be one good way. And even to prove their commutability and all this, the Laxter is very convenient for that. So there
So the previous recipe of what I in terms of this, they get easier a bit from there just by replacing U and by T.
I would say the other way around. So if you know the classical, because this one is missing the things that are like 1 over c. So if you know the quantum, then taking large C limit, you can reconstruct this. But if you know this, then there are still some ambiguities, what is the quantum version, okay?
But one can start the series. Yeah, let's say
It's the leading term. This is the leading term in 1/c expansion, yes.
one can start the series by taking not I1 in this brackets, but let's say I3.
Here?
Yes, the way
It's 135, so
yeah, so I can start, for example, this evolution with respect to T1. Yes, this equation.
yes.
So I can start with not this I1 in the in the brackets on the right hand side.
This should be J, yes, and then it's
Okay, I can start with
no. So these i's, they generate these flows,
different force and
and as you know from again like Poisson geometry or whatever, they are also the conserved quantities of the flows. So if I evolve along I3, the other ones don't change because they are commuting flows. So they are at the same time. This is exactly what this classical geometry tells you, that the generators of time evolution are also constants of motion. So they don't change during the evolution. And this is exactly telling you that these i's have some information about the spectral data that is not changing as you
some kind of system.
for this system of these flows. Okay, so the whole infinite dimensional space of potentials is kind of foliated by this kind of again infinite dimensional subspaces where the spectrum is always the same. So it's yes. So we can think of it as some kind of action angle variables. So if you have like the whole space of all potentials is some kind of fiber over the space of spectral data. And then the fiber is all the potentials that have the same spectral data. So if I fix the spectral data, I can look for potentials which have the same spectral data. And this one is some kind of given by these flows of the potential. Okay, so these flows kind of move inside of this fiber or whatever. This is how you can like think of it like intuitively. Okay? But the important point is that this system, yeah. First of all, the Poisson bracket is exactly the one that agrees with the raster algebra, and then there is it gives you this structural Hamiltonian system, and then I have natural time evolutions in infinitely many time directions, and also conserved quantities along this time. And the analog of these things being conserved is, in the quantum case, the fact that these I3, I5, I7 that they all commuted, and yeah, so that is how this looks kind of in the geometric limit. And I think it's kind of I'm already 10 minutes over time. So I think I can tell you very little about the quantum story, but maybe I should just write the Bethe equations because it was in the title. So I was much slower than when I was, when I was giving it to my thoughts. Yes, it's not only interesting this KDV hierarchy, and so it's not only interesting for physicists, but that there is also this like Kontsevich-Witten story that somehow the intersection theory on Y spaces of Riemann surfaces kind of are governed also by this equation. So this is something that shows up in many different like surprising contexts. So it's interesting on its own. Anyway, so I told you that you have this infinitely many commuting things, and you can try to ask what is the common eigenspectrum. No, what is the spectrum? Yeah, what are the common eigenvalues? Okay, and there is, let me write one other simple model so that you see how kind of simple it is in some sense. How much time do I have? Like, usually?
About -2 minutes, so you can continue.
So I will not write
really,
the screen
I think
share.
about 10 minutes if you.
No, then I skip the, all the nice things and I tell you only. Yeah, there are very nice things. So I can write just right. 1, 2, times. But you will not like appreciate why is it like exciting, because it's took like 8 years until people found this simple system of interaction. Very good. I will write also the other system, sorry. It's two tiny thing. Okay, so there's like old system, like quantum mechanical system of which is called Heisenberg. X infinity. So okay, so I have a copy of like I have chain of m sides, and each associated to each side there is vector space C2 associated to it. So the whole spin chain has vector space C to 2 to n. Okay, that's like finite dimensional space.
So the m is the same as n in the equation.
No.
Counting sections for the model.
Sorry. Maybe I should put here. No, I will. And you like it and here, no?
Yeah.
And I will put n here and.
Yes.
that's
Okay,
right.
yeah.
This is the length of the
This-
chain. And it's different than the number of views.
Yes.
Yeah, okay. Thanks. So, anyway, at every side, I label them like 1, 2, up to n. And at every side, I have this C2, and on C2, I can act with 2 times 2 matrices. So there are these Pauli sigma matrices, sigma 1, sigma 2, and sigma 3. Okay, so there's some kind of complete choice of 2 times 2 matrices, and they act as operators on this Hilbert space output, C2. And then I can consider an operator acting on the full chain, which is just sum of terms, and each term describes interaction between 2 nearest neighbors. And the way they interact is that I take sigma x, sigma 1 in here, times sigma 1 in here, plus sigma 2 here, sigma 2 here, plus sigma 3 here, times sigma 3 here. Because we have this like 3 interaction kind of. It's some operator that makes these 2 things interact, and then you sum such terms over the whole chain. Okay, so it's for every fixed n This is just some 2n, 2 to 2n, no, 2 to n times 2 to n matrix. Okay. 2 to n times 2 to n. So if there are two sides, I will have 2 degrees of freedom here, 2 degrees of freedom here. So the whole Hilbert space would be 4-dimensional. So this will be some 4 times 4 matrix. And it has just integer or half integer entries. Okay, so it's like very concrete matrix.
And why do you have so many Pauli matrices?
Why so many? There's 3.
No, but they are n.
Okay, because I have one acting on every side. Because the Hilbert space is tensor problem of n copies
So
of.
there are some copies in this which I don't understand.
So you can write this arrow. So this arrow in ceramic.
Because I see the sigma 1, sigma n plus 1.
Okay, let me write it for sigma. On the first side, x. Let me call this not 1, 2, 3, but x, y, z. Yeah, maybe this index confused the picture, right? So it's like sigma 1, sigma 2, x plus sigma 1, sigma 2, y plus sigma 1, sigma 2, z. And then I would have sigma 2, sigma 3, x plus sigma 2, sigma 3, y, and so on. And here I would have sigma 3, sigma 4, x, and so on. No? You can imagine how it goes. I have pairwise, so each row is the nearest pair of the sides, and then there are always this. It's like because there is vector of sigma matrix. These 3 together form the vector. They transform under vector representation of SU2. So
And if I plug it into the nth component, I give him index 10 to the sigma.
Probably. I mean, sigma has 2 indices.
Okay,
Sigma has this SO3 index, and then it has the index which says where is it on the spin chain. Okay, and I'm summing over both of these indices. But the lower index I sum between neighbors, and upper I sum via normal metric on SO3 vector representation. So, yes.
Yeah, so is the statement that for any choice, so for any choice of representation of the also object on the left-hand side?
No, I didn't say this statement yet because they are not related.
So we cannot embed an operator from here.
You should just notice if I erase this explanation. You should just notice
The section space is the tensor product of those 5 items.
you should just notice that this equation and this equation are very similar.
So I know that you're doing the equations, the break equations.
Yes. There is like upgraded. There is some symmetry algebra underlying this, which is called Youngian. There is also the Youngian symmetry under this, but it is associated to different Lie algebra, let's say.
Actually, you can make this one also continuous, like the rest of them. It works in many chains.
Yeah, I mean there are some like people study like
So
some
you are
chain
labeling by chains, you are labeling the atoms.
chains are labeling the atoms. Yes.
Maybe kind of ladder with
Which means
Yes.
the position of the.
But it's like different than that I will talk about. But for your question,
Otherwise,
the main difference between these two things is here the interaction which I didn't explain is a rational function of degree 1, and here is a rational function of degree 3. So that's kind of the main upgrade. So you go from degree 1 to degree 3. And this is what looks like 8 years. Okay, but otherwise they are like different systems. It's just that the equations are analogous. So let me explain what are these equations. So I explained to you how to construct these 2 to n times 2 to n matrices that act on this Hilbert space. And the question is, what is their spectrum? Okay, so you can try to, like numerically, whatever, diagonalize them, or if you are strong in linear algebra, you can try to calculate these characteristic polynomials and, try to solve them. But actually, it's very difficult, and especially since the size of matrices is growing exponentially. So it's really like you can do maybe n equal to 10, but then 20 you wouldn't be able to do. Okay, but what Bethe found in 1930s was that if you actually solve this system of m algebraic equations or m unknowns uj, where j runs from 1 to m, then not every, but every nice and good solution of this equation exactly corresponds to one eigenstate of this Hamiltonian, and furthermore, the eigenvalue of this Hamiltonian is some simple function of this. It's something like, let's I don't like to you, and let me look at the exact formula. Something like from J1 to M, 1 over Uj minus 1 over Uj plus epsilon. Okay. Up to some over multiple circumstances. Okay, so for every solution of this equations, good one corresponds to eigenstate of this Hamiltonian, and the eigenvalue is simply encoded in some rational function of these roots. Okay, so this is kind of a general procedure of Bethe ansatz. It's always like translating the like matrix diagonalization problem to some system of algebraic equations. Solutions. There are as many solutions. There should be as many solutions as is the number of eigenvalues, eigenstates there of the Hamiltonian, and furthermore the eigenvalues are given by this. And this is not like the end of the story. There is actually again like infinitely many of these Hamiltonians. So this Hamiltonian is the first Hamiltonian of the whole hierarchy of Hamiltonians. Of course, since we have just finite dimensional Hilbert space, these infinitely many Hamiltonians become related to each other, but you can also increase the size of your spin chain. And then the statement is that there is like infinite family, which is kind of uniform. When you increase this n, and all these Hamiltonians can be simultaneously diagonalized by solving this system of equations. Okay, so this is what goes under the name of Bethe ansatz, and there are different versions of it. Yes, Bethe didn't study it in this algebraic level, but he studied it kind of by in some kind of plane waves that move along the chain, and then he found for what momenta the waves he can find a consistent solution, and he ended up with equations of this type. Okay? And then, like the surprising thing, and the thing I want to conclude with, is that basically after like 80 years, so around 10 years ago, people realized that very similar system of equations also diagonalizes this KdV charges and even much more, conservativities and even much more. So that system of equation looks exactly the same. So I didn't explain you all the letters, but basically here I have this epsilon parameter, which I can rescale away. I can absorb it into U because everything is homogeneous in this epsilon. Okay, and here I was missing for the line for the spin chain. Okay, so this is one parameter. Then the U's are what's called beta roots. So this is the unknowns, and then finally I have this Q. This is like convenient external parameter, which tells me if I want to study, if I want to kind of open the chain or study non-periodic functions of the chain, it's convenient to introduce this extra Q parameter. Like the interpretation of these equations is that we fix one particle, the one that goes with index j in these equations, and I move it around the whole chain, and every time I encounter some other particle, they interact via this phase. Okay, so this term is really like pairwise interactions of the J particle with all other particles. And then I have also some interaction of the J particle with some external fields. This is the only information in the equations that knows actually about the length of the chain. So this is kind of the overall contributions. I go around the circle. And then finally I have this twist, which tells me when I come back, I have this extra multiplication by Q. Okay, so these are the parameters. On the other side, this is the analogous equations which diagonalize this Virasoro algebra generators and much more. And the structure is identical. So again, J particle interacts with all other particles in some hypothetical chain. The interaction is now not given by this degree 1 rational function, but instead it's given by degree 3 function. And these epsilon parameters, now you cannot scale them away, but they know about your central charge, about your representation of the Virasoro algebra. And then, so this is the interaction between the particles. And finally, there is this one more interaction with external fields. So that is just the J interaction with something. and that knows about the primary, about the high space state. Okay, so these numbers AL and epsilon, they are purely fixed in terms of your representation theory, and then basically the Cartan eigenvalues acting on the high space state. And then if you solve these equations, you have collection. So we have collection of solutions, and they label the states in your Verma modules of the Virasoro algebra. This parameter Q has kind of similar interpretation of the list, but it has also one very nice numerical use, which is that in the limit when Q goes to 0, these equations can be solved quite easily because the right-hand side is purely multiplicative. So I can move on all the denominators to the left-hand side. Then when I put the Q equal to 0, the right-hand side is filled. So I really need to solve equation 0 is equal to product of linear factors. Okay, and that's very easy to solve. You just need to kind of branch, like, did I make this 0 or this 0 or this 0, and that gives you kind of solutions. And if you look at the combinatorics of this, what is happening is that you are, so this is some kind of box counting problem. You are building 3D partitions, 3D diagrams in a like corner of the room, and the solutions are labeled by these configurations of boxes. So these epsilons, they tell you if the next box is to the right, to the front, or to the up, and so on. So there is a very nice picture for those who ever saw like this Gromov-Witten invariance in C3 and all these like nice things in math. So there is a lot of nice combinatorics in this, like crystal melting and Youngians and Nekrasov partition function. There are a lot of like nice math behind this, but the nice thing is that it's all kind of captured by these simple algebraic equations. So if you find a clever way to solve these equations, it can be very interesting. Yes. And this is like there is completely different set of Bethe ansatz equations for the same system, and it's not clear how to solve this, but those are related to some differential operators in complex plane with apparent singularities. And if you study monodromy of those things, it also should have the same solutions, but it's very it's not known how the two are related. There is much many unknown interesting things in this story. Okay? But at least now you know how the equations look like. So thanks.
Thank you very much for your nice talk. It was a load of information. When I'll cut it into pieces to put it on TikTok,
Okay,
I'll have hard time. Please, questions.
yeah, I can email you the names of sections.
Yeah, so basically you consider this corresponding solution from various level of the equations. And you mentioned that you don't consider all solutions, you consider only good ones, like what you said you didn't know.
Yes, so this took a very long time. I think for mathematicians, because this things, for example, this problem is something that you can ask mathematicians to solve because it's like well-defined thing, finite matrices and all that. So I think it took also quite a long time, like maybe 50 years, or maybe even not. Like I think in 90s there were like groups of Russian people who finally found some kind of good criteria, because typically this equation has slightly more solutions and they are also missing some solutions. But the easiest statement that I can make is that if there is something that you can call inhomogeneity, there is some extra parameter that you can have associated to every side. And if you do that generically, and if Q is generic, then it's one-to-one, and that's kind of easy to prove. But then you have to study what happens when you try to put this inhomogeneity to 0, and you want to go with Q to 1, because the physically most interesting case. And there, some solutions go to infinity, and some solutions. Okay, there are some like things that you have to really kind of address more carefully. So some solutions are better than the other ones. Typically, you want to exclude, for example, in this picture, you want to exclude solutions where U is going to 0 and solutions where two of them collide. But this is kind of typical example of what kind of social conditions you should add to this thing. There was some kind of hypothesis for physics, it's important what is happening at large n. And they, for example, have conjectured that the most solutions are good, the typical solution is good and so on. So for like this thermodynamic properties for large n behavior, it was kind of okay, but now there are even like very concrete conditions which you can write to get good solutions. On this other side, I don't know such conditions, but I know. So again, physically most interesting case is where q goes to 1. That corresponds to what I talked before. But on the other hand, when q is equal to 0, you can solve it in terms of this very nice combinatorics of these 3D diagrams. Okay, and then what you can do is that you can write immediately the solution. Every beta root, every u corresponds to one of the boxes. Okay, so you can just combinatorially write the solutions at q equal to 0. That's very easy. And then you can just numerically, increase q from 0 to 1, and you can follow the solution. This is called homotopy method of solving the algebraic equations. And if you evolve these good solutions that correspond to boxes in the corner, if you evolve those, then you always stay in good solutions. So somehow there is some kind of like Riemann surface, or I don't know how to really, yeah. I have this Q space, and on top of it, for each Q, I find some discrete set of solutions. But as I change Q, these beta roots of these solutions, the solutions are evolving, and they can have some non-trivial monodromy. There can be some points. If I go around them, the solutions are exchanged, and so on. But the claim is that somehow this kind of algebraic curve is lying over this Q plane, that it knows about the whole representation theory of this Virasoro algebra, and that it doesn't mix the bad and good solutions. So if you start with good solution that you go to 0, and then you go to this physical Q goes to 1 on some curve, then you never mix the good and bad solutions. So that's my working way if I want to find the interesting solution. But it would be much better if there were kind of more algebraic criteria how to decide which solutions are the good ones and which are bad, and that is known here. But here, I don't think anyone really. Also in representation theory, you have you can study the Verma module, or you can study the irreducible quotient, and somehow choices which solutions you take also correspond to whether you want to describe the states in the Verma module or in the simple quotient and so on. So it's like there are choices, and when I say bad solutions, they are bad, for example, if I'm interested only in the simple quotient, but they are interesting maybe from the Verma module point of view. So yeah, but I don't think much has been done. I mean, there is Q deformed story of this, where this function, instead of being additive, it's kind of multiplicative. It's like trigonometric deformation of this. And there, people like Fagin, Muchin, and others, they studied this much more. So yeah, there it's more advanced, and it's kind of very analogous. Okay.
So just to reiterate quickly around this question. So there is a bijection between the solutions of the Bethe equations and the spectrum of H1, which is 2.6.
Modulo some extra condition. Generically, let's say generically, for generically reduced parameters, yes. But for example, one thing that is happening is that because of this being written in terms of this SO3, sigma matrices, there is SO, the global SO3 symmetry that exists here. And typically, the solutions of this, if you exclude zeros, they are only capturing the high split states of the SO3, and then the lowering Ladder operators of SO3, you would act by hand because they kind of escape to 0 or infinity, I remember, in this limit. Okay, so but this is I kind of understood how to get all states.
So but the mode was completely solved. So the
No, there are these additional conditions. So now I think I would say that now it's known, even for this non-generic case, how to make this bijection. In other words, what you need to exclude, which solutions you need to exclude, and how to get all solutions. So there is way, if I write this on one side and this on the other side, it's known which other conditions you have to write to make it one-to-one. Okay, but I don't want to say it because it involves some other things that I can talk about, like skew functions, and there are different things that you have to introduce to even describe. But if you make these parameters this one, and the inhomogeneous, if you make it generic, then it is one-to-one. Okay, so there is kind of generic point in the space of parameters where it is one-to-one, and then the task is how to understand how to make it still one-to-one, even if you go to special points. Okay? And this is, I would say, for this one it's known. For this one, it's very complicated and rich, so I don't think you are anywhere near the answer here.
So conductivity of this ice. So ultimately it reduces to combinatorics of the coefficients in terms of powers of u and prime. In terms of small numbers. So
For small values. Yeah, the problem is always it's easy to check it for low values of these labels for lower powers, but you want to do it, you want to prove it for infinitely many of them. So for that you have to be smarter and you have to use something like this Lux matrix or some more clever method. It's like this pseudo differential operators. There are some like algebraic ways how you can produce these. It's kind of easy. You just take, if you know this pseudo differential operators, you take this square plus u, then you take square root of this, which is some differential operator like derivative plus something times b inverse plus something times b minus 2 plus blah, blah, blah. So there is, if you introduce this formula,
pseudo differential operators on the right hand side, you said that I get simple differential operators.
So that is the algebra of pseudo differential operators, which is something that starts as derivative or some integer derivative, and then you go all the way to infinity with formal negative powers of derivative. Okay, this is some ring, and the coefficients are always some differential polynomials in U. Okay, and in this ring there exists, for example, the square root, and it's like unique. So there is like way how to calculate. You basically like multiply two of these, and you want this to be equal to that, and then determines all these coefficients. Okay, and then if you, and then the way you use the active derivative is also simple. So if you have b alpha u, you can use the, let me write us. Then you can use the Leibniz rule of this. This is sum over k from 0 to infinity. Now I will get confused. U alpha k over k, u k, and f alpha minus k. I think this is correct. No? There should be some kind of Leibniz rule like this. Does it make sense for integers?
And u is only one variable function.
Yeah, that's only one variable. Okay.
But f is more variable.
And now I delete f, and I think it in terms of just like operators. Okay. So you have this, but the point is that now such an expression makes sense even for alpha that is not integer. Okay. And it produces only positive integer powers of the derivative of u, but then on the right you still have this, the negative derivative part in principle. Okay, so this is kind of basic algebraic relation how you manipulate these negative derivatives. Okay, and those allow you. This is just like algebra. Those allow you to calculate square root of this differential operator, and then once you have it, then you can take any integer power. So you have b2 plus b 1/2. Then I take like what was the nth power of this, and then I rest it to the differential part. I just project. I just put all these negative derivative powers to 0, and the claim is that these ones for n running from 1 to infinity exactly produce all these like kind of integrals, for example. So this is like compact way how to write all these things. That's like mathematically there is kind of well developed algebraic theory of these things. Okay, so yeah, and this calculus of pseudo differential operators allows you also to prove the commutativity and all these things quite simply. But it's you have to be clever to figure out that this is the right formalism for you for proving those things. But like degree by degree is very easy to find it and check that there is like unique solution. So, and here you also see Yes, you will also see what happens if
And
n
delta
is even.
is delta self-adjoint. Delta is self-adjoint.
You can introduce a junction also, yeah, this. So, you also see that if n is integer, then this power is just integer power of this, so then the differential part is again just the integer power of this, so they are kind of just powers of this. There was maybe here I forgot, maybe here I should not take the differential operator, but the trace, but I forgot. Maybe there should be trace, and I forgot how the trace is defined, but if you want, I can find it. Yeah, exactly. And that's the reason why if n is even, you don't get anything because it's differential again. Because if n is even, this has no integral part, which is this thing. And then yes, it's as you say. So the trace is taking coefficients. Yes, thanks for reminding me. So of the inverse.
And suppose we take this, just like give you a list.
Yes. Yes. Good. So sorry for this. Yeah, and then this trace has property of trace, you know, the trace of product is cyclic and so on. So that's why it's called trace. I mean, it's not so difficult to. There is a book by Dickey, something like this, like the whole book where he proves all these things algebraically. So, and it's nice because you don't even need to discuss, you know, like the spectral theory, like, you know, the functional analysis. That commutativity of all these things is like purely formal algebraic and doesn't depend on how you choose this, you know, the Hilbert space, whether you are working on a circle or a real line with exponentially decaying solution or not, you know. So that the integrability is kind of local thing and not depending on this space of functions that you consider and so on.
So previously we had this asymptotic generating series for the dimensions in the spectrum of L0.
Yes.
So the asymptotic was something like exponential of constant times square root of the parameter.
Exactly. The parameter was the level, the eigenvalue was 0.
Yeah. So I was wondering, so this asymptotic probably is now to arise in combinatorics somehow.
I mean, so for example,
Does it enumerate anything?
yes. So for example, it can enumerate this configurations of boxes.
So when you were saying that you are interested in like splits in refining the spectrum of those.
Yes. That's
So-
kind of being able to, so that original generating function would tell me in how many ways I can put 5 boxes in the corner room.
But which configuration will give you?
One state. And then I want to somehow be able to distinguish the different configurations of 5 boxes. That exponential is telling me how many configurations. This is like also very good, I can draw a 2-line picture. So asymptotically, you get something that's what they call topological text. If there is a very large number of boxes, then I would get a kind of, you know, 2D shape. And I would get like very large number of boxes that are under some algebraic curve, then this one. For Young diagrams, there is also some kind of limiting shape. So the statement is that if your values of parameters are such that you are studying just ordinary Young diagrams, and also somehow, which is away from this story, then asymptotically you are counting number of boxes that are under this kind of curve, the boxes are getting smaller and smaller. And then that formula is kind of telling you what is the volume of, you know, under this curve, about this curve. Okay. And yeah, asymptotically again, you are typically counting some configuration of these 3D boxes that gives you volume for this thing. And it's very interesting to calculate it. Like, I don't think so much is known, you know, for this simple one is known. They call it limit shape. You know, OpenCore has studied these things in different ways. And the algebraic geometers study this a lot in the context of this Gromp-Witten or what they've done also, Thomas, all these like invariants of Calabi threefolds and so on. Because this kind of physically counting some BPS states, whatever strings in these geometrics.
So the physical theory of the spectrum of L0 is always.
Sorry?
In physically meaningful series, the spectrum of L0 is always.
The spectrum of L0 is infinity?
Is
It's like unbounded, yeah, it's like unbounded, but it's like integer space. Yes, for this, in this CFTs. Actually, what happens, I mean, I did not, if I was sure in PowerPoint,
It has infinitely many elements.
if
Yeah.
no, I mean, it is of the format I wrote, it's like, there are 2, 3, the simplest example is this, the in a function, which is just counting number of Venn diagrams. So that's like product, 1 over product, j from 1 to infinity, 1 minus q to j. This is the simplest function that is in CFT describing what this free boson. Okay, and the q expansion of this is 1 plus q plus 2q squared. You see, I'm counting Venn diagrams, no? So then plus 3 q cubed plus I think 5 q to the 4 plus 7. You just count how many diagrams you have.
So the specification of dimensions in the spectrum of L0 of some can be checked.
For the value of L0 given by the exponent. So this is telling me 7 vectors of L0 equal to 5.
So this is 3 bosons.
3 boson. And the counting is very easy because you have your 5 place plates is annihilated by some aj of j is positive, let's say or 0, and then the other ones act as the value operators. So in you apply some next one, there is associated algebra of this space, which is aj, ak is j divided by j plus k 0. Okay, this is just the algebra with the boson, and now I check a certain number of times with a minus 1, let's say n1 times, then 10 times with a minus 2 and so on. Okay, so this is kind of after using one variable width to order the generators. This is kind of how a basic choice of basis, Fock space. And then the L0 eigenvalue is given by n1 plus 2n2 plus 3n3 and so on. Because actually, you can define Virasoro generators also in this Fock space. Roughly L0 is sum a minus n a. Okay. I don't know how much you see solve this. Okay, anyway, it's counting a1 with weight 1, a2 with weight 2, and so on. So if I have n1 a1s, n2 a2s, and so on, then the L0 weight is given by this. Okay, and now counting. So now if you fix the eigenvalue n of L0, you are asking in how many ways I can write n as a sum of positive integers, like how many ones, how many twos, how many threes, and so on. And that is something that you can write as Venn diagrams. Okay, so for example, for 5, I can write it as 5 or 3 plus 4 plus 1, 3 plus 2, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, or 5 times 1. Okay, so there are also I'm missing something 3 plus 1 plus 1. So I wrote it probably, no, correct, 7, 1, 2, 3, 4, 5, 6, 7, and here I have 7 states with n equal to 5. Okay, so the partitions are labeling the states in this boson Fock space, in this free boson, and the generating function of number of these is this. This is again clear, no? Because I have 1 over 1 minus q times 1 over 1 minus q squared, 1 over 1 minus q cubed, and so on. And if I now expand this in geometric series, I get 1 plus q squared plus q to the 4th plus q to the 6th, and so on. So then if I take n Taylor series term n1 Taylor series term here, and n2 here, and 3 here, and so on, I get exactly kind of this decomposition. So the coefficients of q to n are exactly calculating number of ways that I can write n as sum of non-negative integers, and that's labeled by Venn diagrams. Okay, so this is all these things are very elementary. If you try for yourself for 10 minutes, you will see. So this function is counting number of Venn diagrams, and it's inverse of this direct eta function. It has very nice modular properties. And now if you use this modular transformation of it, so there is a formula which connect. So if I write Q as E into pi I tau, where tau is shape, of the complex torus, the modules of this genus one.
Tau is
Very
in
much
upper
different.
plane.
Sorry?
Tau is in upper plane.
It's upper half plane, yes, it's in upper half plane. This is the real axis, it is upper half plane. So I write Q as this, and then you can kind of cut the torus on this circle or on that circle, and the corresponding taus are related by, you have either tau or -1/tau. And physics kind of doesn't depend on how you cut it, if you cut it like this or like that. So somehow the partition function should be invariant or at least nicely covariant under this transformation, which is true. So there is some transformation eta of tau and eta of -1/tau is regulated. And I don't remember, there is some power of imaginary part of power. There is some kind of nice transformation property between these two. And you see that here, the q equal to 0 limit corresponds to tau going to I infinity, while this q goes to 0. While q goes to 1 corresponds to tau goes to 0. Okay, so there are these two limits.
The square root of this tau.
Yeah, there is some.
Eta goes nicely on this minus basis.
Yeah, there is some something square root of this imaginary part of tau. Some you can find it on
If you
Wikipedia.
transfer squares of tau, square roots of tau, then it's the eta just change the sign.
Okay, Tomáš, sorry for interruption. I think we pretty much exceed our time. So thanks again for your nice answers.
You stop it or not?
Not really.
I don't know. I just so there is formula like this which connects the q going to 0 if you're going to 1, and